Hi, everyone. I'm Anca Dragan, and I wanted to share with you today our latest thinking on how to get robots and AI systems more broadly to assist people. And let me first share what I mean by assistance here by giving you three example tasks that we've recently been working on. So one of them is assistance with navigation. So imagine you're visually impaired and you're trying to navigate a house and you can't directly perceive the scene in front of you. But looking at the scene from top down, what you're really trying to do is go somewhere, but you don't know exactly where you are and how to get there. And so how can an assistant guide you and help you get to where you want to go? This is one of the assistance questions or tasks that we've looked at. Another example is for users with severe motor impairments who are, say, trying to type a sentence in their email. And what we did here is we set up an eye gaze-based interface that presents a set of words to the users, like here in a circle, and waits for the user to look at their desired word, and then takes pictures of the users through their webcam. And given this webcam image, the interface tries to predict which word the user wants to type. And we've also been working with UCSF Department of Neurology with a patient with quadriplegia there who has an ECOG array mounted in their motor cortex. So for him, instead of gaze as input, we're using his brain activity that we record with the ECOG array to help map this signal, what he's thinking, to the word that he wants to type. So that's example number 2. And my third example that I want to give you is, say we want to be able to operate a robot with complex dynamics. In this case, we were looking at a very simple version of this, which is the Lunar Lander game, the famous Atari game. So what you want to do is you want to land this in between the flags and not crash, but you can see that it's really hard to do so because this lander, this craft is really difficult to control. And these are people without any motor impairments, but still it's really difficult for them to actually land in the right spot and not crash. And so can we enable them to do so and to do so better and faster? So in these tasks, users have some policy that maps the state that they're in to actions that they take, that they kind of command through their interface. And then a decoder can translate their actions, their input, onto actions that the robot can execute. For instance, with the lander, that would map keyboard input that you provide to lander controls for the craft. But unfortunately, these actions are, as we saw in the lander, really noisy and suboptimal. So a typical way to do assistance is that instead of just executing these actions AT directly, these decoded actions, assistance usually approaches the problem by trying to infer the user's goal. What are they trying to do ultimately? So where are they trying to land in lander? Where in the house are they trying to navigate to in the navigation task? What sentence are they trying to type? And then the assistant would take actions on their behalf that better achieve that goal. So that's a typical paradigm. I've worked on this paradigm. Many other folks have worked on this paradigm, but there's some challenges with it. So the same suboptimality in user actions that prompted us to want to do assistance in the first place makes it really hard to figure out what the user's goal is sometimes. Like in the lander games here, people overshoot their goal to the left or to the right by quite a bit. And so you can see on the bottom of the slide there, for these two examples, the distribution over goal locations that the assistant has inferred. And when the person overshoots to the right, like it happens here, what you see is that the robot, the assistant agent has inferred a distribution that puts a lot more probability mass on goals that are actually to the right of the correct goal, the true person's goal, which is here in green. And so sometimes it's really hard because of the suboptimality. It gets in the way from actually figuring out what people want, and then we assist them with the wrong thing. And even if we infer the correct goal, which we do sometimes, What's bad about it is that we're taking away the person's autonomy by completing the task for them and essentially largely overriding their input. So here in this example, you can see that at some point, like here, the assistant kind of takes over and pretty much overrides what the person does and just bam, lands the craft, which is beautiful and great in some ways, but it strips the person away from their control authority, from their autonomy, and it just does the task for them, and that can feel pretty underwhelming as well. And so we've been wondering, could we, instead of correcting the user's actions to make them optimal for their goal, could we instead somehow enable users to take better actions by themselves? Could we just assist in the sense of getting them to take the right actions instead of us sort of looking at their actions saying, now I'll do this other thing instead? What would that look like? And it sounds a little bit like a holy grail, but we have some ideas that I'll share with you today. So the question is, could we go from this override that we're doing at the end here to somehow the users being able to act optimally so that we can just execute the actions that they're providing? And to answer this, we had to step back and ask ourselves, well, why are users taking suboptimal actions in the first place? Where does this suboptimality come from? And one answer, and it's just only one answer, is that part of the suboptimality comes from the fact that they don't get to see the state of the world directly. So this picture is somehow wrong. Why is the user action suboptimal? Because the user is not looking at ST, they're actually getting observations, OT, about the world, much like robots do. And they're acting not based on ST, but based on the belief that they form, the estimate that they have about what the state of the world actually is. And that belief could be wrong. And if that belief is wrong, then that leads them to take suboptimal actions because they're acting based on the wrong information. Now, why on earth would that belief be wrong? Well, plenty of reasons. Here are some examples. They might not be able to pay attention to the many different sensors all at the same time in some tasks. It might be difficult to pay attention to everything on your screen, for instance. Lens distortions can cause users to overestimate distances to objects. We do this every day when we drive. And we know that these things are issues because otherwise optical illusions wouldn't be a thing, right? All humans misestimate the state of the world right here in this example, for instance. And that's because of biases and shortcuts in our perception system. So that's why we end up with beliefs that are not entirely accurate. And so if we want users to take better, closer to optimal actions, then our idea was that instead of correcting their actions, we should see if we can correct their beliefs. As in basically in turn, that enables them to take better action. So the problem is we can't just incept a belief into the user's head. So what does it mean to correct their belief? But what we can alter in many tasks is the observations that they receive. And so by messing with the observations, we can mess with the belief and hopefully induce better beliefs. And so the key insight in this work that we did is that the full observations are not necessarily the most informative about the state. And that's true, especially when they're processed by incorrectly by the user due to systematic biases in their perception. And so there might be other observations, OT tilde, that we should be giving them instead that would be more informative, that would be better at leading the user to have the right belief. So the way we operationalize this is by using an automated assistant to process the full observation on behalf of the user. And the assistant performs state estimation unencumbered by systematic biases or perception difficulties that the user might have. Then the assistant provides the user with a modified observation, OT tilde, that when processed by the users suboptimally, leads to them having a more accurate belief than if they just saw the raw unfiltered observations. So we're hoping that this belief BH that they form based on OT tilde is more accurate than the belief they would have formed otherwise if they just saw OT directly. So formally, what we try to do is minimize the KL divergence between the assistant's beliefs and the user's beliefs. After the assistant processes the true observations, it synthesizes this modified observation OT tilde that it thinks will make the user believe in the same state as the assistant. That will induce a similar belief in the user when the user processes it with their model BH of processing observations that the assistant has when the assistant processes the true observations OT with the correct model that the assistant has, which is B. So now, why is the assistant's model correct? Why is this? Why is the assistant belief sort of the target here, the holy grail? Well, because robots don't suffer from information overload and they can apply Bayes' rule correctly. So it seems fair to say we're going to do sort of the best estimation we can. It's not like we know the state, but we are doing the correct estimation. So we have the correct belief we should be having. And then what we're trying to do is get the person to have the same belief as us. What's hard here is that we don't have access to the user's internal state estimation process. This BH hat, this thing that maps observations and actions historically to distribution over states, that is, we don't have access to that, that's in the person's head. So what we do is we propose to learn that from demonstrations of user actions, collect users acting and see if we can backtrack what their state estimation process might be. And so what we do here is we model the likelihood of the user taking a particular action, given a history of observations and actions so far, by marginalizing out the state. So we integrate over the state. And what that does is it helps us break down this likelihood of the user's action into two components. On the one hand, we have a near optimal policy, AT given ST. We can compute that given the task, and a parametric representation of the user's belief estimation process, that BH, which we can model as a neural network. So what's nice about this is that we can compute the near optimal policy, we can compute this term, and we observe user actions. And so we can set this up to back derive what belief model here is consistent with the data. And the way we train this is by optimizing the user's estimation model to maximize the likelihood of the user actions that we observe. Once we have this, we have our user model, which means we can figure out what observations O tilde to give them that will hopefully lead them to better beliefs. And in turn, the hypothesis is better actions. And so we apply this to the assisting people to navigate indoors tasks. And again, they can't see directly where they are. They can't see the scene in front of them. Looking at the top-down view, they're trying to reach a position in the middle. If they think they're in one corner of the house, but in reality, they're in a different corner, that leads to trouble. That leads to them taking suboptimal actions. And so we instead have an agent guide that can see the user's egocentric scene and figure out what objects are around. And then the guidance that this guide provides, in our case, there are many options here, but in our case, we decided to have the guide tell the user about what's around them. So the guide would say, you know, you're around this or that, there's this object next to you. And a default guide would just kind of tell you about the stuff around, maybe all the stuff around, which is a lot of overload. And you'd update your understanding of where you are based on that. And you try to navigate. In contrast, our guide selects objects to tell you that are going to be informative about where you are. And that tends to result in more accurate user beliefs. And as a result, the user taking less time to reach their goal. My favorite example of this wasn't in the navigation task. It was actually in the lunar lander game. So we looked at a version of the lunar lander game where we made it really difficult to see where the lander is. And we added this horizontal sort of tilt bar to help the user perceive the angle of the lander. And then we looked at what the guide, sort of the assistant, learned to display to the user. And what the assistant learns to do is to exaggerate the tilt of the lander to compensate, it seems, for our apparent inability to correctly assess the tilt. So here what's actually happening on the right, what you see by default on the left, and then what the assistant is showing you, and I'll play this again, what the assistant is showing you, which is just really a much more exaggerated version of this tilt. And essentially, by the agent, by this assistant lying to you about how tilted this lander is, and it's a total utter lie, right? It's not as tilted as it's showing. Users are able to keep the lander more level and do their job better. So it seems like what's going on is that if you have a slight tilt that's hard to detect, you might not detect it, and then you might not counter rotate enough. In contrast, when the assistant decides to exaggerate the tilt, then it's much easier for you to detect that. And it seems like you're not over-correcting. It seems like you're kind of correcting just the right amount. So the assistant finds sort of the angle that ends up working with that. And indeed, it's a different angle for different people. And so overall, we've been getting creative with how to enable users to take good actions on their own, which we think is a very empowering way to do assistance. And in the remainder of our time together, I wanted to share two quick alternative ways through which you could improve these actions that users command beyond improving their beliefs. So if we want the user's actions to be good, another, and this is perhaps much more obvious as an avenue than the belief trick, another avenue is to improve this decoder that the user has, that basically that we're using to map between the interface that the user has access to, like a keyboard or gaze when controlling their action, and the actual actions in sort of the physical space that you can execute. So remembering from earlier in the talk, we were looking at this sort of gaze-based interface, this typing task. The question is, how do you train this decoder, right, that has to go from gaze or even brain machine interface to a commanded word, which is, that would be the action that you'd actually execute. How do you end up with this decoder in the first place? And the idea is, can we actually make that better? And if we make that better, then the actions that people take end up being better. So it's a very obvious way to intervene on the decoder side. So how is this decoder trained? Well, the standard approach is kind of this calibration approach, where you calibrate this interface with supervised learning. So that requires a new user to provide this paired data of inputs and actions. But this can be really time consuming and disruptive. And actually it drifts over time, even for the same user. So our patient from UCSF with quadriplegia, for instance, the readings we get at the beginning of the session are actually very different from the readings we get at the end. Well, so there's this drift in the interface, even over the course of the day or even a few hours with the user, you see this sort of drift. And that's why these decoders, in a sense, are stale. And that's what is another reason why the actions that we're getting out of them are not necessarily the best actions. So our idea is that instead of calibration, we could initialize the system with this default interface that is designed for an average user, but then customize the interface to a new user by actually getting them to type and observing what they do. And the trick is, how do we get any feedback? As the user types, when they mess up, they're going to have some undo action, like a backspace in this case. And these undo actions, these backspaces, are essentially naturally occurring feedback on the accuracy of the decoder. And so they enable us to actually train the decoder online through reinforcement. And so instead of learning a decoder once and keeping it fixed, what we can do is we can make user actions better by evolving the decoder online. And the way we propose to do that is by leveraging this backspacing or undoing actions as a source of implicit feedback that tells us what we were just doing was wrong and we shouldn't do it anymore. And so we can learn from that. So our method from learning from these undoing actions, these backspaces, is simple. We present a set of words to the user. We take a picture of the user's eyes through their webcam, if this is the gaze-based interface, and then feed this input to our selection policy. We sample an action from this policy. The user sees the action. The user compares it to their desired action and then decides whether or not to backspace. If it's the wrong action, they'll backspace. And this decision to backspace naturally provides our system with the feedback that it can use to derive a reward signal and train the policy through reinforcement. So in particular, we train this reward model to be a binary classifier that predicts the likelihood of these backspaces. And what lets us sort of do this, now we have a reward function, so we just optimize it. What lets us actually use the default interface and build on top of it is we use that default interface as a prior policy and use the backspace likelihood model to update that prior to a posterior distribution, to a posterior policy. And this does not make any assumptions about the type of user input. And so in addition to conducting some experiments with gaze input through a webcam, we also tried this with our patient at UCSF who used their ECOG brain computer interface to provide input to the system. And I have to say that this was by far the most exciting part of this project, even though, as you can see in the picture on the top left, this patient was only seeing 4 words and had to decide on one of them. So it was much more simplified, but nonetheless, we saw that just kind of sticking to the default kind of calibrated decoder and skipping this online improvement ended up with significantly lower accuracy for them. And interestingly, the default interface, it never actually predicts the top. So you know how there's these four words, you can see them here. It never predicts the top one. And so that leads to a 0% recall rate for that action. And this is most likely due to this drift that I was mentioning. So due to sort of distributional shift in the user inputs over time. In contrast, though, online learning achieves 70% recall on the topmost button. And that's good news because it suggests that it can recover from this drift and it can overcome these challenges. So that was really cool to see. I mean, it was all, choose one of 4 words over time, but by doing this learning and adaptation online, we're able to make it slightly easier for him to do this type of typing. With gaze input as well, we ran a user study. This was 12 participants, and we found that learning the reward model from online user feedback substantially improved the performance of the default non-adaptive interface. We also found that it is more interesting maybe that users for whom the default interface performed particularly poorly also were the users who tended to benefit more from online learning. What we see is that by learning the decoder online and by correcting the user's beliefs, which is what we were talking about earlier, these are both ways through which we can empower users to take the right actions or closer to the right actions on the system without the system having to figure out what their long-term goal is and override their actions. And now to wrap up, I want to give you one final idea for how to achieve this type of assistance that we're striving for. And the thought for this idea came to us when watching users play Lunar Lander. If you look, it's a really rich game. What can I say? We've gotten a lot of ideas by watching people play Lunar Lander. So if you look at what's happening here, the lander becomes so unstable that, and it ends up crashing, right? That it's really hard for the user to do anything. So no matter what their goal is, no matter what they'd like to do with the aircraft, it's really hard for them to do that, to achieve that, because they quickly get to states where the lander is essentially out of control. There's not much that they can do. And so the thought was, let's fix that. We don't really need to infer their goal and help them. What we need to do is get the system to be more controllable so that they can help themselves. So we need to increase the user's controllability, we say, over their environment. That is their ability to affect their environment through the actions that they take. And so we formalize this notion via information theoretic empowerment. So this is the mutual information between the user's actions and the resulting states. And we call this assistance via empowerment. So low empowerment situations are those where the user, can't really do much. They're bad. High empowerment situations, you have a lot of options. It's easy to reach many states. And so those are good states to be in. And so the way we get people to be more in high empowerment states is by having the assistant directly optimized for the user's empowerment, and we use reinforcement learning to do that. And so in this is an example result from Lander. Even though the assistant cannot observe the goal flag, so has no idea where it is that the person is trying to land, empowerment leads to the stabilization that in turn leads to improved success rate within the user, because now they can actually control the system to go where they want. And this is sort of naturally emerging out of just having the assistant optimized for the user's empowerment. So that's kind of a third way to get at this problem, which is overall, we have these alternatives to typical assistance. And in a sense, I've talked about three of them. I talked about beliefs, I talked about improving the decoder online, and I've talked about just doing assistance by empowerment. But they're all sort of getting at the same issue, that instead of figuring out what people want and then having a smart robot sort of help them with that, it seems possible to find ways to empower people to take good actions by themselves and get the task done on their own. So that could be getting assistance in processing the information they're getting. It could be making the system adapt over time to user changes, or it simply could be optimizing for the users to be empowered to do whatever they want. But either way, I think this is a paradigm of assistance that's worthwhile looking at as an alternative to the typical thing we do. So with that, I'd like to thank you, and thanks to my collaborators on this work, and especially the students who actually did the work, as well as the UCSF folks who have been really, really instrumental, obviously, in getting this done. So thank you very much.